For as long as we've been able to write, we've had this deep-seated need to keep secrets. Whether it's military commands or just personal letters, that desire to communicate privately has sparked this secret war of wits. It's a timeless cat-and-mouse game between the people who make codes and the people who break them. And that's the story we're diving into. So, let's start our journey in ancient Rome. I want you to picture this. You're Julius Caesar. You're commanding these huge armies across a massive empire. You have to get orders to your generals, but any messenger you send could be captured. If one of those messages gets intercepted, well, that could be the difference between a huge victory and a total disaster. The stakes just couldn't be higher. So, what's the move? What do you do? How do you make sure that even if your message falls right into enemy hands, the information inside stays locked down? This was the exact problem Caesar was up against, and his solution gave us one of the most famous secret codes in all of history. He used this brilliantly simple trick. The idea is to take a normal, readable message, we call that the plain text, and use a special method to turn it into this jumbled, unreadable mess, which we call the ciphertext. Now, to an enemy soldier, this is just gibberish. But to a Roman general who knows the secret to unlocking it, it's a crystal clear order. This method is what we now call the Caesar's cipher. It's a type of substitution cipher, which is just a fancy way of saying you're swapping each letter for a different one. In Caesar's case, he just shifted every letter 3 places forward in the alphabet. So an A becomes a D, a B becomes an E, you get the idea. The secret that unlocks the whole thing is that number, 3. That's the key. It's simple, but for its time, it was incredibly effective. All right, so Caesar's simple little shift cipher actually introduces us to the fundamental ideas that are behind all of classical cryptography. Think of it like the basic toolkit that every codemaker and every codebreaker absolutely has to understand. Let's just get the lingo down real quick so we're all on the same page. The plain text is your original message. Easy enough. The ciphertext is the scrambled version. The cipher is the recipe, the method you use to scramble it. And the key, well, the key is the secret ingredient in that recipe, the one thing known only to you and the person you're sending the message to. For centuries, pretty much all secret codes were built on 2 basic moves. First, you've got substitution, which is what we saw with Caesar. You're literally swapping out letters for other things. The second move is transposition. With this one, you keep all the original letters, but you just jumble them up into a new, confusing order. Almost every classic cipher you'll ever see uses some mix of these 2 core ideas. But of course, for every person trying to invent an unbreakable code, there's always someone else trying to break it. This is where the other player enters the game, the cryptanalyst, the codebreaker, the detective of secret writing. So how in the world do you break a code when you don't have the key? Well, you look for clues. And it turns out, simple substitution ciphers like Caesar's leave a massive, glaring clue behind. The secret weakness is that every single language has its own unique fingerprint. In English, for example, the letter E shows up way more than any other letter, followed by letters like T and A. This pattern is the fingerprint. So if a codebreaker gets a long encrypted message and sees one symbol appearing over and over and over again, they can make a really good guess that that symbol probably stands for E. This whole technique is called frequency analysis, and it is the absolute kryptonite of simple substitution ciphers. So once the codebreakers figured out frequency analysis, the game was on. The codemakers had to evolve. They desperately needed a way to hide that linguistic fingerprint and make their codes much, much tougher to crack. And the solution they came up with was ingenious: the polyalphabetic cipher. Instead of using just one secret alphabet, what if you used many of them? What if the letter A was encrypted as a D the first time, but then a K the second time, and maybe a W the third? This method, which is guided by a secret keyword, completely flattens out those letter frequencies. It basically erases the language's fingerprint. And this right here, this is the tool they use to pull it off. It's called a Vigenère square. Now, I know it looks a little complicated, but the idea behind it is actually pretty straightforward.
It's basically 26 different Caesar ciphers all stacked on top of each other. You and your friend agree on a secret keyword. Let's say it's secret. To encrypt your first letter, you use the row that starts with S. For the second letter, you use the E row, and you just keep cycling through the keyword. This was a massive leap forward in security.
So this back and forth battle, this constant one-upmanship, it went on for centuries, always with substitution and transposition at its heart. But then, the digital age arrived and completely changed the game, taking these ancient ideas and launching them into the world of modern security that we all rely on every single day. See, modern computers don't think in letters. They think in ones and zeros, or bits. So modern cryptography isn't about scrambling A's and B's anymore. It's about using incredibly complex math to protect long strings of binary data. We're talking about everything from your emails to your bank account. And modern ciphers handle all this data in two main ways. A block cipher is kind of like translating a whole paragraph at once. It grabs a big chunk of data and encrypts it all in one go. A stream cipher is more like a live interpreter, translating one little bit at a time right as it comes in. Both of these methods are built on those same ancient ideas of shuffling and swapping, just, supercharged with crazy powerful mathematics. The final and maybe most crucial evolution was in how we handle the keys. For centuries, you used what's called a symmetric key, one single secret key that both the sender and the receiver had to share. But modern cryptography gave us something incredible: asymmetric keys. This system uses two keys, a public key that you can give to anyone and a private key that you keep totally secret. Anyone can use your public key to lock a message and send it to you, but only you can unlock it with your private key. This is the magic that puts that little padlock on your web browser and protects your messages on apps like Signal or WhatsApp. So, what's the big takeaway here? It's that this ancient game is far from over. The tools have changed, for sure. We've traded paper and cipher wheels for incredibly powerful computers, but that fundamental fight between the code maker and the code breaker, between secrecy and discovery, is exactly the same as it's always been. And all of this leads us to one last really big question for our modern lives. In a world that's literally built on data, where everything we do leaves some kind of digital trail, and where code breakers have almost unimaginable computing power, is any secret ever truly 100% safe?